Okay, this is part 2. We are looking at discrete random variables, and we're working on this question with Ichiro, who was a baseball player for the Seattle Mariners, and we verified we had a discrete probability distribution. We drew the graph in StatCrunch, so here's our graph, and now we need to compute the mean and interpret the mean. So again, remember the mean is, well, I'm going to come up here so we can see this. The mean is the sum of each value times its probability. So in our case, it's going to be 0 times 0.1677 plus 1 times its probability, 0.3354, plus 2 times its probability, plus 3 times its probability, plus 4 times its probability, and finally plus 5 times its probability. So when I multiply those and then add them up all together, I get 1.63 rounded to 2 decimal places. So that would be the mean. And notice that that matches up with the mean we got here. Okay. And so in any given game, Ichiro would average 1.63 hits per game in this baseball season. Okay, now we want to compute the standard deviation. So remember the standard deviation, so it would be the square root of the sum of x squared times p of x, and then minus the mean squared. So in this case, this would be, this is going to be a big old honking thing here. So you'd have 0 squared, so x squared times the probability of 0, which is 0.1677, plus 1 squared times its probability, 0.3354, plus 2 squared times its probability, 0.2857, plus 3 squared times its probability, 0.1491, plus 4 squared times its probability, 0.0373, plus 5 squared times its probability, 0.0248. Then you would minus from all that 1.63 quantity squared. Again, you're taking the square root of all that, so you need to make sure you calculate that value inside the square root correctly. Then take the square root, and this will give us like 1.17. Okay, and that will match up with our standard deviation we're given here. Okay, it's probably going to be, there's going to be much more precision here, well, a little bit more precision here because potential rounding errors and so forth. But that's the standard deviation. Okay, so part E now. What's the probability that in a randomly selected game, Ichiro gets 2 hits? So what's the probability of 2? Okay, if we come up here, probability of 2 is just right there, 0.2857. And that's his probability. So very straightforward on that question. Okay, part F, so this was E. Part F, what's the probability that in a randomly selected game, Ichiro got more than 1 hit? So the probability of more than 1. So 2 ways we could do this. More than 1 is 2, 3, 4, or 5. So we could add up the probabilities of 2, 3, 4, and 5. Or we could use the complement, which is 1 minus the probability of getting 0 or 1 hit. And this would require less calculations. So this would be 1 minus the probability of getting a 0. And then you'd also subtract the probability of getting a 1. So this would be 1 minus, and those probabilities were 0.1677 and 0.3354. Okay, and I get 0.4969. Whoops, not 6669. And that'd be the probability that Ichiro gets 1 or more than 1 hit in a game, I should say, not 1 or more than 1. Okay. So let's look at another interpretation of the mean of a discrete random as an expected value. So we're using this idea of expected values. So because the mean of a random variable expresses what we would expect to happen in the long run, it's also called the expected value. That's why you hear this. So we'll write E of x. The interpretation of the expected value is the same as the interpretation of the mean. So when you see expected value, that is the mean. And here's one example of where you could use an expected value. If you're a life insurance company, okay, you sell a $250,000 one-year term life insurance policy to a 20-year-old for $350. Okay, and according to the National Vital Statistics Report, the probability that a male survives that year is 0.998734. So the probability that a male lives for the entire year is 0.998734. So there's a very small chance that the 20-year-old male will not live through the year, whether it be illness or accident, or the case may be. But we want to know what's the expected value of this policy, because for anyone who lives, they're going to keep the $350. But for someone who unfortunately passes away, they're going to pay out the $250,000. So they need to figure out, okay, how much am I going to pay out per policy, and then that will help them determine cost that they should be charging for the individual every year. So here would be the expected value of this random variable x. Okay. So the expected value is going to be so first we're going to look at if someone were to die, then the value x is going to be, they're going to have to pay out $250,000, but we assume that the individual paid the $350, so that's going to be $249,000 and change. Is how much they would, and it's going to be negative because they're going to be a loss. They're going to be paying that out, and then we times it by the probability. Well, the probability that someone dies is going to be 1 minus the probability that a 20-year-old male lives. Okay, and so this is like our x and our p of x for someone who dies. They have to pay out $249,650 at a very, very small probability. Plus now, okay, the x now is if they live, they pay $350 at probability of 0.998734. Okay, and that's again for the people that live. So this is someone who died, and this is someone who lived. Okay, when I multiply these out and then I add them together, I get $33.50. So here, what this is telling us is that the expected value on any policy in the long run is they'll make $33.50 on each policy that they sell. So I'll say expect to make $33.50 of profit per policy sold. Okay, and so if you sell, a million of these policies, then you would take $33.50 for each one policy that you expect to make, and times it by a million. That would be your expected profit. So again, we have to look at the two circumstances here: the probability, someone passed away, and the probability someone lived, and take those probabilities times by the amount of money the company would either make or have to give out, and then add those together. Okay, so last one. So in the game of roulette, a player can bet or can place a $5 bet on the number 17 and has a 1 in 38 probability of winning. If the metal ball lands on 17, the player wins $175. Otherwise, the casino takes the $5. So we want to know what's the expected value of the game to the player. And then if you play 1,000 times, how much you expect to lose, because if you're gambling, the expected values are going to be negative. People who set up these games are not unintelligent. They are very, very intelligent individuals. So here's our expected value. So our expected value is going to be, well, if I win, I make $175, but the probability of winning is at 1 in 38. Okay, so this is kind of the winning case. Plus, if I don't win, so I'm going to lose $5, and the probability of losing is the remaining 37 out of 38, which is a negative 0.26 loss per game. Now that does not mean that each game you're going to lose 26 cents. This just means over the long run, you're going to lose 26 cents per game that you play if you play this for a long time. So over 1,000 games, then you are going to play 1,000 games with an expected loss of 26 cents per game, which is negative $260. So you are expected to lose $260 if you play this game over and over 1,000 times. Again, that's not to say that's exactly what will happen, but that is what we expect to happen. That's one of the reasons why we call it an expected value. So that wraps us up for this section. Here's a look again how we did those calculators in StatCrunch. So if you need to double check that, feel free to look this over. But I did go through it in the video on how to graph those, and you can see the means and the standard deviations. But I appreciate your time in watching this video and hope you have a great rest of your day.